All right, so let's get started. Before we dive into lecture material, I wanted to first point out this project that we're going to be doing throughout the remainder of the semester. If you look on our homepage here, we see this new badge that's opened up for this Chemistry and Careers project, and we have this series of assignments under this project here. So just to take a step back to explain, so basically what you're going to be doing is you're going to be finding somebody in your field of interest and conducting an interview with them about the role that science and specifically chemistry plays in that field, right? So everybody's here for a specific degree path. Some of you may be chemistry majors where it's pretty obvious the role that chemistry plays. Other people are going into other sort of like health science fields where the role that chemistry plays might not be that obvious. So why are you here in this class? That's kind of what this project's going to help you explore, is why chemistry competency is going to be important for you and your career in the future, okay? So step one is by the end of this week, you're going to have come up with some career ideas. What jobs would you want to have after you graduate? And you're going to find people, look online, find email addresses for people to get their contact information. And then by the end of next week, you're going to have sent them messages trying to line up an interview for the remainder of the semester. Okay? By the end of this month, you have to have an interview lined up, right? So you have to have an interview confirmed. There's a month that you have to do it because not everybody's going to say yes, right? So this may be something where the very first person you email says yes, and great, you're done. You might have to then move down the list before you get a yes, right? So you have a month to line up that interview, and then you have another month in order to actually conduct that interview. Once you get your interview lined up, you're going to come up with some interview questions, and then by the end of November, you have to have actually submitted that interview to this assignment here, okay? So to be clear, you're going to be recording this interview. You can do it in person or on Zoom, but what your submission is going to be is a video of that interview that you've conducted, okay? Once we get all that, we'll then peer review other people in the course's interviews to get an idea of why chemistry is important for that career field, okay? So this is a project that you'll have these full 2 months to do, because again, it might take you a second to line up an interview. That's why we have a bunch of time to do it, all right? Cool, so in that same respect, don't schedule your interview for like the day before the assignment is due, because something might happen. It might need to be rescheduled, and that's why we're given this huge amount of time in order to do it, okay? The other thing is, if for whatever reason nobody that on your original list has said yes, you have a full month to line up that interview. You're just going to try something else, right? So it doesn't matter if it's your first selection or it's something that you improvise later. I don't really care. You got a full month to line something up, all right? And then another month in order to do the interview. If you've taken a course with me, a Chemistry 1B course in the past, you might have done this same project. You're more than welcome to use that same interview subject, but you do have to conduct an interview in these next 2 months in order for you to meet that assignment criteria, right? You can't submit an old video that you've recorded previously. If you already have a relationship with somebody, you're already in an internship or something like that, then absolutely take advantage of that. I'm perfectly okay with that. If you do already sort of have something that you're doing working within the field, that's great. I think that's exactly what you should be doing at this point. If you don't, this is a great way to sort of network. You got an excuse to be emailing these people and to be setting up this relationship, right? You can use this as an opportunity to hopefully line something up in the future. People have taken this assignment and turned it into an internship because they got their foot in the door by conducting this interview, all right? So that would be great. At the end of the day, you're going to walk out of here with this piece of paper. It's not like they just throw jobs at you because you have a degree, right? Your networking and the sort of stuff that you do building those building blocks in here will help you getting a job once you get outside of here as well, right? So start that network, try to get internships, get into research positions, whatever it may be. You want to sort of start that stuff before you leave this institution. So again, this is going to be kind of a nice little excuse to be starting that networking. All right, so let's now dive into our course material, if this works. All right, we're going to start by doing some review. We talked about these oxidation and reduction reactions. So everybody take a second. If we took this aldehyde here and treated it with lithium aluminum hydride and then followed it up with that acidic workup step, what would our product be that we expect from this reaction? Right, so we can reduce an aldehyde to a primary alcohol. We could have used either of our reducing agents to do it, but that's what lithium aluminum hydride would do. All right, and we looked at our reaction mechanism for these reactions. And we're going to learn another reaction here today that's really, really similar. So we're going to practice this. If we have our aldehyde and we add in aluminum hydride, remember the lithium's not really doing anything for you. All right, and what was so special about those hydrides? We said that in these hydrides, hydrogen plays the role of what? The nucleophile or the electrophile? The nucleophile. That's the whole shtick of these hydrides, is we have this nucleophilic hydrogen, which means that my aldehyde here is my electrophile. And specifically, what's the electrophilic site in this molecule? All right, take a look closely at this molecule. Try to find where that electrophilic site is, where that lack of electron density is. Remember, an electrophile is electron poor. Which one of my atoms here is relatively electron poor?
Carbon.
My carbon, specifically
Carbon.
the carbonyl carbon, right? The one at the base of that carbon-oxygen double bond. Okay, so given that we've identified our nucleophile and our electrophile, try to give me the first step of our reaction mechanism here. All right, so nucleophiles attack electrophiles, but remember, I'm not allowed to start my arrow here because my arrow has to start at a pair of electrons. So I have to start my arrow at that hydrogen-aluminum bond. That's my pair of electrons. And I can't stop with just that step because then I would be breaking this carbon's octet rule. So remember, what makes that electrophilic carbonyl carbon such a good electrophile? Not only does it have a lack of electron density because it's in this polar bond with that more polar oxygen, but it's also got this built-in leaving group pair of electrons here, which means that when it gets attacked, it never has to break its octet, right? It can just kick this pair of electrons up onto that oxygen. Okay, so what we have here are what we call an alkoxide ion, a negatively charged oxygen. And we're kind of stuck here until we do that second step in our reaction, right? So that would be step one, adding in that aluminum hydride. As soon as we take that and move on to step two, We've now added that to some dilute acid solution for the sole purpose of protonating that oxygen, giving us that alcohol product. All right, so step one creates that new carbon-hydrogen bond, breaking that old carbon-oxygen bond, and then we just got to protonate our negatively charged oxygen in that second step to get our primary alcohol here. All right, so this was our reduction reaction. We had both, we should be able to predict the products of these reactions, but we should also know our reaction mechanisms, keeping in mind that these reducing agents, these hydrides, have these nucleophilic hydrogens. Okay, we're going to move on to a new class of reactions here, and we're going to see these kind of over and over again throughout the course. These are what are called Grignard reactions. Okay, a Grignard reaction utilizes what's called a Grignard reagent. And these Grignard reagents are kind of weird. These are what we call organometallic compounds. All right, if we pick apart this word here, organometallic, we got two parts to it. The organo, an organic molecule, but an organic molecule that contains a metal in it, which is very unusual. We don't see that very often at all. So an organometallic compound, this is an organic molecule that contains a metal. All right, so let's look at an example here. It turns out that if you take something, an alkyl bromide, so for example, 1-bromopropane, and you add in magnesium, like literal shavings of magnesium metal, those magnesium atoms will insert themselves between the carbon and the bromine. All right, so now we have this very rare carbon-magnesium bond creating what we call a Grignard reagent. So a Grignard reagent is an organometallic compound with this magnesium bonded to a carbon atom. All right, again, kind of weird. When we're talking about our covalent molecules, our organic molecules, we're talking about non-metals, right? So now we're adding a metal into the mix here, a special class of compounds we call organometallic compounds. Okay, let's look carefully at this new carbon-magnesium bond here. Carbon is an element that we don't think about as being very electronegative. Right? And that's because we're always comparing it to all the other non-metals. So compared to nitrogen or oxygen or a halogen, carbon is relatively low on the electronegativity scale, right? But metals, those things living on the exact opposite side of the periodic table, those have really low electronegativities. So in this bond here, carbon is actually the more electronegative atom, meaning that there is a lot of electron density sitting on my carbon atom and very little sitting on that magnesium, right? So because magnesium is a metal, metals not holding on to their electrons very tightly, not very electronegative. In this carbon-magnesium bond, carbon is the more electronegative element, all right? So what we have is a lot of electron density sitting on that carbon atom, which means it's going to be playing the role of what? A nucleophile or electrophile? nucleophile, right? Lots of electrons mean nucleophile. So these Grignard reagents, what's so special about them is that we have these nucleophilic carbons. Not an atom we see playing the role of a nucleophile very often. All right? Usually carbon's not the more electronegative element, but since we got this special organometallic bond, carbon's actually able to pull a lot of electron density onto itself. Right? Our carbon has lots of electron density from that polar bond with magnesium. All right, so these reactions, they're going to involve this Grignard reagent here, and this Grignard reagent has this nucleophilic carbon. All right, so let's see if we can't predict what's going to happen. Let's do a reaction. Between this aldehyde here and our Grignard reagent. All right, I will say that this reaction, much like our reduction reactions, occur in two steps. One is you add in your Grignard, and then secondly, after that reacts, you have to follow it up with another one of those acidic workup steps. And we're going to try to predict here what our product is of this reaction. All right? In order to do that, we're going to go ahead and look at our reaction mechanism. Right, so let's see if we can't ration through here what's going to happen in our first step. Okay, as we said, our Grignard reagent plays the role of the nucleophile, right? And specifically at that carbon bonded to my metal, that's where my nucleophilic site is. It has a lot of electron density. Which means that this other thing, my aldehyde, is going to be playing the role of the electrophile. And if I look carefully at that aldehyde, what do I think our electrophilic site is going to be? That electrophilic carbonyl carbon, right? I said we're going to drill this into our heads by the end of the semester. We're all going to be chanting in our sleep, electrophilic carbonyl carbon, right? This carbon right here with its relative lack of electron density. So I have this carbon nucleophile in my Grignard and this carbon electrophile in my aldehyde. Everybody take a second and see if you can't put in the electron pushing arrows based on what we discussed previously with our other reaction mechanism, right? Direct analogy to what we were looking at before with our hydrides, but now we have this new Grignard reagent here. All right, nucleophiles attack electrophiles, but make sure your arrows don't break any rules about where they need to start and end, and octet rules. All right, so nucleophiles attack electrophiles. So I'm just going to go like this, right?
No.
No, what's wrong with this? So, base of my arrow cannot be at this carbon atom. It has to be at a pair of electrons. So specifically, it's going to be that pair of electrons between my carbon and my magnesium that's doing my attacking, right? So my base of my arrow has to be at a pair of electrons. And then I can't stop here because I would be breaking this carbon's octet rule. So whenever our carbonyl carbon gets attacked, that built-in leaving group pair of electrons jumps up onto that oxygen atom. All right? So to be clear, this arrow up here, this is a regular old bond breaking arrow. That pair of electrons, that bonding pair is going to become a lone pair. This one down here is a bond breaking arrow because I'm breaking that magnesium carbon bond. In fact, at this step, or after this step, my magnesium and its bromine come flying off. All right, but I'm also forming a new bond, so it's a bond breaking and formation arrow. I'm forming a new bond between my nucleophilic carbon and my electrophilic carbon. All right, so if I'm going to draw my reaction here, or rather draw my product of this step, I have a new bond between that electrophilic carbon and that nucleophilic carbon. We have a new carbon-carbon bond. All right, and before we move on, we're going to go back up here to our Grignard reactions and just make note that our Grignard reactions, they create carbon-carbon bonds. All right, that's going to be true of all of our Grignard reactions. It's one of the things that makes those Grignard reactions so powerful, Grignard reagents so powerful. Okay, I'm not done yet here. We should note that there's something missing on this blue carbon. What's missing on that blue carbon? My oxygen, right? So I don't have a carbon-oxygen double bond anymore, but I still have a carbon-oxygen single bond. Right? That pair of electrons jumped up, giving that oxygen a negative charge. All right, so before we move on to step 2, let's just note here, I have my new carbon-carbon bond here between my electrophilic carbon and my nucleophilic carbon. Right, so my molecule here, I started out with this 3-carbon aldehyde, and now I've attached on this 3-carbon Grignard. So I've grown my carbon backbone. All right, and my formerly carbonyl oxygen now has that negative charge. We're going to move on to step 2, which is where we add in those hydronium ions, some dilute acid. All right, everybody's going to take a second and finish off. What's going to happen when that alkoxide ion rather, comes into contact with that hydronium ion? What's my product going to be? Right, well, that alkoxide ion is a strong base, so it will take a proton away from that acid. So then what's my functional group of my product? Name of the chapter, right? Alcohols, right? So again, we have a way to synthesize alcohols using these Grignard reactions. Importantly, what's going to make these Grignard reactions very powerful, but also kind of a pain in the butt, is that we have a new carbon-carbon bond. So we're going to be growing our carbon backbone in these molecules here. So we're always going to get a product that's bigger and uglier than what we started out with. What's going to be really important here then is counting carbons from the left-hand side to the right-hand side. I color-coded mine even to make it obvious what was what. But a good double check that you always want to do for these Grignard reactions, because we are growing our carbon backbone, is just a quick count. 1, 2, 3, 4, 5, 6. All right, 1, 2, 3, 4, 5, 6. Make sure you have the same number of carbons on both sides. Okay, so just to finish off our summary here, we have our balanced chemical equation up here, but then we also have our mechanism for these Grignard reactions. All right, and you just want to point out how closely analogous this is to our reduction reaction mechanisms as well. There we had a nucleophilic hydrogen. We had to start our pair of electrons at that hydrogen boron bond or hydrogen aluminum bond. All right, now we have this nucleophilic carbon. We have to start our electron pushing arrows at that carbon magnesium bond. We get this same alkoxide intermediate here, and we have that same last step of protonating that alkoxide intermediate in order to get our alcohol product. Cool. All right, so these reactions, again, we're creating new carbon-carbon bonds, so it's easy to get lost of how we're going to connect these things together. So we're just going to do some practice for the remainder of this period here with these Grignard reactions. I have two Grignard reactions here. You're going to take a second and tell me what the product is of these reactions. right, so I'm going to do my color coding here. I'm going to note my electrophile are these 4 carbons here, my ketone. And specifically that electrophilic site is that carbonyl carbon. My nucleophile are these 3 carbons, and specifically that nucleophilic site is my carbon bonded to that magnesium. So when I draw my products here, I'm going to need to include all 7 of these carbons. So start with my 4 carbons for my electrophile. Importantly, since this was my electrophilic site, when I draw that new carbon-carbon bond, on the other side has to be that nucleophilic site from my Grignard. So I'm going to decorate that with those 2 methyl groups, so I have those total of 3 carbons in there. And then lastly, I need my functional group here, that carbonyl oxygen, still bonded to that same carbon, but now it's not a carbon-oxygen double bond, it's a carbon-oxygen single bond. Right, so that gives me my alcohol functional group. Okay, and then just a quick double check. I should have 1, 2, 3, 4, 5, 6, 7 carbons on the left-hand side, meaning I should have 1, 2, 3, 4, 5, 6, 7 carbons on the right-hand side. All right, again, I've created my new carbon-carbon bond between that electrophilic carbon and my nucleophilic carbon. Okay, I'm going to play the same game down here, and this is actually a good illustration of why these Grignard reactions are so powerful. A lot of times we have a lot of restrictions on what types of molecules we can use in our reactions. Your Grignard reagents are very, very flexible. So, for example, this is an sp2 hybridized carbon instead of an sp3 hybridized carbon, and both work perfectly fine. All right, so these Grignard reactions are quite flexible, which is why they're quite powerful. So again, color coding my carbons from my electrophile. I'm going to need to include these 4, and specifically my electrophilic site. I got my 6 carbons from my nucleophile, and I'm going to identify my nucleophilic site. All right, start drawing my products here. So here's my 4 carbons from my electrophile, and specifically this one here was my electrophilic site. So now I'm going to draw a new bond, a new carbon-carbon bond. On the other side must have been that nucleophilic carbon. So I'm just going to fill in there with the rest of my benzene ring. Cool, so I've attached those 4 carbons to my 6 carbon nucleophile here. And then the last thing that I need to include is that functional group. That oxygen is still bonded to that formerly carbonyl carbon. It's just now, instead of being a carbon-oxygen double bond, it's a carbon-oxygen single bond. Okay, so here would be my alcohol product from this reaction. Cool, so given an aldehyde or a ketone and a Grignard, we should be able to determine what our alcohol product is going to be. All right, the other thing that we're going to work on is going the other direction. So if I'm given an alcohol here, and I'm telling you that this was a Grignard reaction, meaning that we used an aldehyde or ketone and reacted it with a Grignard reagent to make this alcohol here, what would we need to do it? All right, so everybody's going to take a second and identify an aldehyde or ketone that they could use and a Grignard reagent. There's actually 2 possibilities here. We'll go through them both, but just focus on giving me one here. All right, but how could we make this alcohol using a Grignard reaction? All right, so how am I going to do this? Importantly, when I look at this product here, there's one thing that I can be super confident about, which is that this carbon right here at the base of my alcohol, that must have been my electrophilic site in this molecule, or in this reaction, right? Meaning that this carbon here is going to be my formerly carbonyl carbon over here on my product side. But again, there's actually two different combinations that we could use, because I could say either that this bond on the left was my new bond, so that's my new carbon-carbon bond that formed, meaning that this is my nucleophilic site, or this is my new carbon-carbon bond that formed, meaning that this would be my nucleophilic site. All right, so either one of those would work. Did the bond on the left form or the bond on the right form? Which one's the new bond in my reaction? Either one of these would work. So either it's these two carbons over here, whoops, that make up my electrophile. So this ethanol here, all right, where again I have two carbons in my electrophile, meaning that these two carbons over here were my Grignard nucleophile. Okay, so we could have used a 2-carbon aldehyde and a 2-carbon Grignard to form our 4-carbon alcohol product. Or if instead I'm going to say that this bond right here is my new carbon-carbon bond, that means that these 3 carbons must have been my aldehyde, my electrophile, all right, specifically with that 3rd carbon being that electrophilic site. So then this 1 carbon over here would be my 1-carbon Grignard, methyl Grignard over here. Either one of these combinations would give you that same alcohol product. All right, so we're going to do one more, but then this time I want you to try to figure out what both methods are that would make this particular alcohol. Again, there's 2 ways to do it. Try to come up with those 2 ways of creating this alcohol product. right, so again, what I know for sure looking at my alcohol is that that carbon at the base bonded to that oxygen, that must have been my electrophilic site in this reaction. All right, so that means that either this bond over here on the left or this bond over here on the right were my bond, my new carbon-carbon bond that was created. If it's the carbon on the left, or rather if it's the bond on the left, that means that this was my nucleophilic site. Whereas if it's the bond on the right, that means that this is my nucleophilic site. So kind of cleaving this molecule at that bond there, okay? If I'm going to say that that right fragment was my electrophile, that would mean it's this 5-carbon ring. With this aldehyde group coming off. Right, where that carbonyl carbon is my electrophile. So that means these 1, 2, 3, 4, 5, 6 carbons here. Okay, so then this would be my nucleophilic fragment here. All right, and specifically this carbon here has to be the one bonded to my MGBR. Okay. All right, or we're going to say that it's the bond on the other side. That's my new carbon-carbon bond. That means that these 5 carbons here have to be my aldehyde. Where that carbonyl carbon was my electrophilic site. So that 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons, okay? And then these 5 carbons over here are going to be my nucleophile fragment. All right, and in particular, this carbon here that I've identified as my new carbon-carbon bond, that has to be bonded to that MGBR. All right, so using either of these two methods, we could synthesize that alcohol using a Grignard reaction. Cool, all right. We're going to call it there. We are going to pick up, we still got some discussion of alcohols to go. That's what we're going to be doing for the remainder of this week.